Hi, this is Professor Fernandez. This is the first video in lesson 7. So the topic here is limits approaching infinity, and I'm going to do two examples from Calculus Simplified to help you make sense of that. So the first example, example 2.33, has two parts, and really it's a variation on a theme. So the function here is 1 over x, whereas over here it's 1 over x squared. Very similar functions. One of them is effectively 1 over x squared is the square of 1 over x. And the limit we want to evaluate is as x goes to infinity for these functions. Okay, a few quick things about x going to infinity, just as an intuition and a concept. First of all, infinity, right? Where is infinity on the number line, right? Infinity is sort of all the way over here in a very conceptual sense. I can't put it specifically anywhere as I could 0 and 7, for example. And negative infinity is all the way over here. There is conceptually nothing to the right of infinity. So you will never see a limit that looks like this, approaching infinity from the right. That makes no sense. There's nothing conceptually to the left of negative infinity. So a limit like this would also make no sense. So left and right limits when infinity is involved is not something that we worry about because it just doesn't make sense in terms of what the concept is all about, infinity. So that's just a quick little orientation to what we're doing on the x-axis side. So then let's investigate this first limit here. So what happens to the function 1 over x as x goes to infinity? This is a new concept in what we've been doing so far in this series. Thus far, we've talked about a variety of techniques for evaluating limits. We could use all of them here. We could try to graph the function. We could try to make a table of values. Okay. We could try to use some sort of simplification, some sort of algebraic technique to simplify the function. So these are the basic three. Or, of course, we could try to just substitute in the value. Substitute. However, not everything applies in this new infinite context, right? We cannot substitute in x equals infinity. You may see somewhere floating around the internet, maybe perhaps even in a math class near you, where people would say this is equal to 1 over infinity, and then use the quote formula that 1 over infinity is 0. I highly discourage you from falling prey to this sort of thinking. So I will not do that. Part of the issue is that, again, infinity is not a number. So I can't divide by something that's not a number, right? It doesn't make sense in a calculus course. There are certain things that we divide by functions, but at a particular x value, those functions become numbers. So ultimately, there has to be some number that is floating around for me to actually claim that the answer is some number that involves infinity, like 1 over infinity. Okay, so sorry for the long-winded explanation. Just want you to not fall prey to some of these other ways of explaining this limit. So what are we going to do? So I'm going to start here and also lean on this to convince you that the answer is indeed 0. So let's start with a table of values. All right, here's my x, and here's my function 1 over x. X is going to infinity. That means that x is getting progressively larger, right? So I could start with, like, let's say 1. And the reason I'm doing this is not only to get intuition about the function, but also to get comfort, I should say, with what the function is, right? So if x is 1, the function is 1 over 1, which is just 1. If x is 2, the function is 1 over 2, which is just 1/2, 0.5. If x is 3, the function is 1/3. So at this point, I hope you notice that whatever value for x I put in, the output is just the reciprocal. Okay? The reciprocal. 2, the reciprocal is 1/2. 3, the reciprocal is 1/3. So if x is going to infinity, which is increasingly large and positive without bound, then the function 1 over x should be like 1 over a very large, and I mean very large number. Okay, great. So what does that approach? Well, let's go back and do decimal form here. At x equals 2, 1/2 is 0.5. At x equals 3, 1/3 is 0.33. And if I did x equals 4, continuing the table, I would get 0.25. So you can see the general trend in these numbers, right? 1, 0.5, 1/3, 0.25. They are decreasing to 0. So indeed, 1 divided by a very large number is very close to 0. and limits are about trends. So our best guess using this tabular approach is that the answer to this limit is indeed 0. Okay, that turns out to be the correct answer. So now let me verify that in a different way, or I should say maybe add more support to the arguments that it's equal to 0. How would we do that? Well, we can use one of these other techniques. How about we use the graphing technique? So if I were to graph the function 1 over x, right, the graph looks basically like this. It has a vertical asymptote at x equals 0. And you know, if I'm looking at the function y equals 1 over x, there is no x value that I can substitute in here to get y equals 0. If I try to solve this equation, there is no solution. So the graph on top never crosses the x-axis. The graph on the bottom never crosses the x-axis. In fact, as the reading for this lesson indicates, the fact that we took a limit as x goes to infinity and we got a number means that that number is the horizontal asymptote, y equals 0. So this is another way to find horizontal asymptotes using calculus. Take the limit as x goes to infinity and or x equals negative infinity, depending on whether you want to find the horizontal asymptote or you're just asked to find the limit. If you get a number, then that number is the horizontal asymptote, right? So again, so this graph decreases since we're going this way. We're going that way for x getting closer to infinity all the way out there. So this graph decreases to 0. Okay, never actually gets to 0, right? Again, the important part to remember, right? The limit approaches indefinitely, does not arrive. And remember, we can't solve this equation for x. So there is no x value at which the y value is 0. That's part of the reason we call it a horizontal asymptote. Although a little asterisk, there are functions, one of them is discussed in the textbook, that cross their horizontal asymptotes. This is not that function, or one of those functions. Okay, so having talked a lot and at length about this example, let's go ahead and try the second example, B over here. You'll notice that there's not much that's going to change, right? This is the limits, again, as x goes to infinity of 1 over x squared. So if I try the same approach again, make my little table, 1 over x squared. If I start with x equals 1, okay, x equals 2, I get 1 over 2 squared, I get 1/4. So we can see that actually this function is decreasing faster than the previous one, right? At 1 over x equals 2, the y value was 1/2. I'll try one more. I get 1 over 3 squared, 1 over 9. So indeed, these numbers still have the same behavior. This is 0.25. This is 1. This is, I don't know, a third of a third, so I don't know, 0.1 something. I don't want to calculate it right now. You can see that the numbers have the same behavior, right? They are continuing to decrease toward 0. So our best guess for this limit is, again, 0, which again would tell us that y equals 0 is a horizontal asymptote of this function. Indeed, if we graphed this function, we would see a graph that looks like this, right? So the previous graph, 1 over x, looked like that. So when you square the 1 over x, which is how you get 1 over x squared, all of these negative y values over here turn positive. So that's one way to think about how the graph of 1 over x squared looks like without needing a graphing calculator. Okay, and it also explains, again, in a visual way, why this limit is 0. The function is decreasing towards 0 as x is increasing toward infinity. Great, so we got 0 for this limit. We got 0 for that limit. There we go. All right, the last example I want to talk to you about here uses a very, very different way to determine the value of the infinite limit. So let's take a look at that example. How about the function x over x plus 1? Okay, so I'm going to give you, I think, let me count the ways, 2 different ways to do this example. I'm not going to lean on the table. We could do it with a table, and it would get us toward a guess for what the limit is. We could graph the function, but in the interest of introducing you to some other techniques, I'm going to talk about 2 other ones. The first one is what I'm going to call a growth argument. Okay, so I'll zoom in here. So let's take a look at the function x over x minus 1. All right, x is going toward infinity. Infinity is like, a concept. It's not a number, but we think of it for all effective purposes as a very, very, very large number. So when x is really, really large, and positive, large positive x, okay, then I'm trying to draw a very long approximates symbol. Then, x remains x, but the denominator, if I have a really, really huge number like a trillion, and I subtract 1, it's still pretty much a trillion. It's a trillion minus 1, but it's pretty close to a trillion, okay? So if I then look at what I'm left with, I have x over x, which would cancel out to 1. My usual caveat here, so long as x is not 0, but I'm very far away from x equals 0 because I'm assuming that x is very large and positive. So what have I shown? I've shown that this function is approximately equal to 1 when x is large and positive. This is an example of what's called a growth argument. Why is it called a growth argument? Because what I did is in the numerator, I thought about how fast does the numerator grow as x goes to infinity. It basically grows like the linear function y equals x, kept that. How fast does this function grow? It basically grows like the function y equals x. It doesn't matter that there's a 1, that just shifts the graph down a little bit, by 1 unit. And then the thing that I have left, I simplify to 1, and then I have this nice little takeaway, which is that this function gets very, very close to the function y equals 1 as x goes to infinity. So that should be enough to tell us that our guess for this limit is 1, which again means that because we've obtained a number as a result of the limit as x goes to infinity, this y equals 1 is a horizontal asymptote of this function. Great. All right, so how would I have found this limit another way? So, this growth argument was approach number 1. Let me show you approach number 2. Approach number 2 is a more systematic way to do this and also applies to more complicated functions. Like if this was a quadratic expression, this was a cubic one, this approach I'm about to show you would come in very handy. So here's what you do. You take the function, you divide by the highest power of x in the denominator. So again, this works especially well for polynomials. It doesn't work as well for other functions. So x minus 1, the highest power of x, is x. So I'm going to divide the denominator by x. Great. If I do that, I also have to divide the numerator by x. Again, ignoring the domain issues because we are going to be very far away from x equals 0. In the numerator, I get x over x, that's equal to 1. In the denominator, I get x over x from this division, which is 1, minus 1 over x from this division. Great, so my function is 1 divided by 1 minus 1 over x. So that is literally just an algebraic manipulation. So it does not change the value of the limit. So my original limit is the same as this limit. Oops, I should have put a 1 over x there. Okay, and then now the point of this is that it's kind of a limit law problem, right? So the numerator is just going to keep going to 1. It doesn't matter that x is going to infinity because the numerator doesn't depend on x. This part, same deal. This is just a 1. That doesn't go anywhere as x goes to infinity. And then how about 1 over x? Where does that go as x goes to infinity? Well, we just did that up here. 1 over x as x goes to infinity tends to 0, right? So we put that right down there. And we finish this up, 1 over 1, which is 1. We get the same answer that we did before, using a very different way. All right, so again, this is the second approach. Works especially well for rational functions. Polynomial divided by polynomial. If you want to find the limit as x goes to infinity of a rational function, then you look at the denominator, find the highest power of x. If this were x squared, then I would divide everything by x squared, numerator, denominator. And then you simplify the algebra, and then you reattempt taking the limit. What this will do, this technique, this number 2 approach, is that it will turn the question of finding the limit of a rational function into effectively what happened down here. The question of combining limits of functions of the form 1 over x to a power, x cubed, x to the fourth, something like that. And that's part of the reason, if I zoom out here, the method to this madness, why I started off doing these first 2 limits. Because if you know these basic limits of 1 over x squared, 1 over x cubed, so on and so forth, then they will come in handy when you're evaluating limits of rational functions using this second technique.